Hello again, everybody, and welcome to example 6 on page 141. And this is another example of using the Gram-Schmidt process to build an orthogonal basis, but what's different about this example is that we're in a more abstract vector space. Okay, instead of talking about Rn, we're talking about polynomials of degree 2 or less. Okay, and you might remember this is an inner product space, but with a very different inner product than a dot product. In particular, we defined, or one way to define an inner product on a space like this is to define it to be the integral of the product of the two functions that we're talking about from 0 to 1. Okay, so orthogonality in this vector space is going to mean that we take the integral of the product of the functions, we get 0. All right, well, how do we do this? How do we build an orthogonal basis for P2 of R? Well, we need to start with a basis that we already know. So what would a nice basis for P2 of R be? How about the standard basis? Okay, so 1x and x squared. Okay, we know that that's a basis for P2 of R. Okay, and we'd like to replace it with an orthogonal basis. All right, so if we use the Gram-Schmidt process, remember that using that formula, it's conventional or customary to call those three vectors W1, W2, and W3, the vectors in our starting set. Okay, and we're going to replace those with polynomials V1, V2, and V3 that are orthogonal. Okay, that's our goal here. So if we start with the basis step, V1 is just going to be W1, which is 1. Okay, so we'll start off that way. And we now want to calculate V2. Okay, so I'm going to be just writing down the formula from theorem 6.4 and running through it. You can look back at that page and confirm that what we're writing down here matches that. So to calculate V2, we want to take W2, which is x, okay, minus the inner product of W2 with V1, which would look like this, over the length of V1 squared. Okay, and I'm going to make a comment there. So this notation, that's just another way of writing the length of 1 squared, the inner product of 1 with itself. Okay, times V1, which is 1. Okay, that's the calculation that we need to do here. Okay, and then we remember that the inner products that you see here and here are really integrals in this space. All right, so the inner product of x with 1 is just by definition the integral from 0 to 1 of x times 1 dx. Okay, and the bottom, we've got the integral from 0 to 1 of 1 times 1 dx. Okay, we're going to multiply that by 1. Okay, and I'm trusting that you can do those integrals. Okay, and if you do, if you integrate x from 0 to 1, you're going to get a half. You integrate 1 from 0 to 1, you're just going to get 1. So if we fill that in, this all collapses down to x minus a half, which should be our V2. Okay, now a comment here. So this fraction 1 over 2 that we have, that's a ratio, and so if we left our V2 the way it is, it might complicate our future calculations. So it would be nice if we had a polynomial without a fraction in it like that. Okay, so I want to make an observation here. So V1 and V2, they're orthogonal to each other. The Gram-Schmidt process guarantees that that's true. So would that change if we took this x minus 1/2 and scaled it, multiplied by a scalar? Would that change the fact that they're orthogonal? If you think about it, it wouldn't. And so we're allowed to scale, to take this V2 and multiply it by a convenient number. What would be a convenient number here? Okay, how about 2? Because if we multiply by 2, it's going to knock out that 2 in the denominator. All right, so we don't like our V2, so I'm going to put a little tilde over it, and we're going to replace it with a new definition of V2 that's going to be obtained by just taking 2 times that V2 tilde. So 2 times x minus a half is going to knock out that fraction and just turn it into 2x minus 1. And as we just discussed, doing that is not going to change the fact that these two vectors, V1 and V2, are orthogonal. That's what we're interested in. Okay, So we've got 2 out of the 3 vectors that we want. Okay, and we're ready to calculate v3. Okay, and this is going to go back again to the theorem 6.4 formula that we have. So to calculate v3, we're going to start with w3, which is x squared, minus the inner product of w3 with v1, okay, over the length of v1 squared times v1. Okay, and then there's going to be a second term, inner product of v3, or I'm sorry, w3 with v2 over the length of v2 squared times v2. Okay, that's just the Gram-Schmidt orthogonalization formula. And then we remember that all of these inner products are just integrals. So we're going to get the integral of from 0 to 1 of x squared in the top, the integral from 0 to 1 of 1 squared in the bottom, times 1. Okay, and then over here, integral from 0 to 1 of x squared times 2x minus 1. Okay, over the integral from 0 to 1 of 2x minus 1 squared. All of that times 2x minus 1. Okay, and then you would need to calculate these 4 integrals. And again, I'm trusting that you can do that. Okay, you'd be welcome to use a calculator or Mathematica if you wanted to. And if you do, here's what you're going to end up with. Fill in those 3 integrals and you're going to get 1/3 times 1 there. And then over here in the second term, you would actually get a 1/6 in the numerator and a 1/3 in the bottom. Those are the value of those 2 integrals. Okay, just one step away here, simplify that down. We're going to get x squared minus 1/3. And then 1/6 over 1/3, that simplifies down to 1/2 times 2x minus 1. Okay, and if you simplify that, just do all the algebra, this comes down to x squared minus x plus 1/6. Okay, and again, we see that we get a 1/6. That's kind of an ugly number to do calculations with, so we can do what we did before and maybe tilde this v3 and say we're going to replace it with a scale. Okay, which isn't going to change the fact that it's going to be orthogonal to the previous vectors. And so we'll call v3 what would be a convenient thing to scale it by. In this case, multiplying by 6 would be convenient. That's going to knock out that 1/6. And so if we multiply our v3 tilde through by that, we're going to get 6x squared minus 6x plus 1. Okay, and so there is our third and final vector, and we have built ourselves an orthogonal basis, which looks like the following. Beta equals, and I'm just going to list the 3 vectors, v1, v2, and v3 that we found. Okay, and if we've done everything right, that should be our orthogonal basis. Okay.